And it's like someone would like sign. I kind of
Yeah, I know. I'm gonna buy them one. I just figured out the best.
Today, I'm going to, in just a couple of minutes, dog paddle over the Mariana Trench of evidence that it is the poor who will disproportionately suffer from the damages of climate change. And then I'm going to turn to discounted utilitarianism, what Professor Furvé talked about last time again. And I kind of spent the weekend on this, and so I'm really curious about the reaction to it. I have a different way of presenting this, and I think that the material is sufficiently embedded in our decision-making in this country that it's worthwhile for a citizen of this or any other country, for that matter, to know about it. And so, and I think that the concepts involved are subtle enough that it can be difficult to assimilate from any one presentation. So mine will come out a kind of different way, right? So let's just, you let me know at the end whether or not you get it. Okay? First of all, if you want to know about the impacts of damages from climate change on the poor, I recommend that you download this thing. It's only a year and a half old. It's called the Shockwaves Report from the World Bank. And this is absolutely chock-a-block. It's a couple hundred pages, and it's chock-a-block full of stuff. It's easy to, if you ever have to research anything on this, write a paper or anything like that, this is sort of one-stop shopping. So I'd recommend it. These graphs are all from it. And I'm going to just make the obvious point that the poor are disproportionately vulnerable. The first one here is what happens if there's flooding in a bunch of different places in Bangladesh, Honduras, and Mumbai. And the answer is the poor. These are the assets or income lost or affected up to 100%. These are the poor and these are the non-poor as defined in each country. And lo and behold, when there's like a big flood, the poor lose a larger fraction of their assets, so it's much more difficult for them to recover. This is the proportion of the expenditure of the household income on food in a bunch of different regions, for the poorest to the most wealthy. And of course, the poor spend a disproportionate amount of their incomes on food. This will be really important when we talk about violence and climate change, because food price shocks turn out to be one of the best predictors of social violence historically, all right? And so for instance, the Arab Spring blossomed in countries where the poor spent more than half their income on average on staple foods, whose price all of a sudden doubled, meaning they couldn't feed their families. And then they went over, right? So, this graph simply shows from the same shockwave report that we expect under a bunch of different scenarios the daily calories available per capita to not grow as fast and can even diminish. And this is in the face of rising affluence and rising demand. So the evidence is that there will be food shortages, and that's the shortages come from food price shocks. And finally, this is the food price rises, changes in the poverty rate because of food price rises predicted under different scenarios of food price changes in a bunch of different countries. And what you can see is that under global warming and the food price shocks predicted under them, you get big increases in poverty from that source alone. So we're going to return to this thing repeatedly. There are many, many damages from climate change that disproportionately impact the poor. But in my view, none of them are as important as this particular feedback. The impact of food prices on nutrition and how that leads to a poverty cycle. And we'll find out violence. Okay, so That's it for the poor for right now. And it's because I think this issue is one where I talked to a bunch of you after the lecture last time, and a bunch of you were still confused about this material. And so I want to return to it, to this notion of discounted utilitarianism that we, after all, use around the world to compute what's known as the social price of carbon. And we then use that, ostensibly, to set policy. And this is now political football, in that you get an administration like the Trump administration that doesn't want to have climate mitigation. They make assumptions about that lead to a social price of carbon that is very low, meaning that you don't have to do much to mitigate it under our current laws. And I also want to point out that Professor Flurbe did a really good job of talking about where the ethics is in this formula. And usually they talk about it in the shape of the so-called social utility function. But as you pointed out, it's in every part of the formula. I want to underscore that throughout the presentation I have for you. So let's start from the basics again and build back up to this thing slowly. The first thing is that we're going to define consumption and in year T as this function, CT. It's the consumption in year T. And it's basically the amount of money you spend on goods and services in economics. Traditionally, this is what it is. It's dollars available for expense and consumption, right? But it's also supposed to include quantities that aren't usually monetized that you also care about, all right? And care about enough that you would actually pay for them if you could, all right? And I want to emphasize that this whole area, this whole sort of set of goods that are not usually monetized is always acknowledged by economic analyses, but it also often always goes with a statement that so many of these are difficult to monetize and we don't know what to do about them. And so we're just going to do this analysis at first by leaving most of them out, okay? And so that's where the problem comes in, is that you always then get an underestimate if in fact the things that you care about are damages, right? So consumption is supposed to value not just money spent, but also enjoyment or suffering from all nexus impacts. The impact on you of a species extinction, the loss of a traditional livelihood by an Inuit person, the sense of failed stewardship by an evangelical Christian. How much would you or they pay to avoid each and every one of those outcomes? How much are they worth in sort of dollars and cents? Now, it's really hard to estimate these things. You can actually ask people what you would pay. And the problem is that if I keep going to the average person and asking, would you pay for this, would you pay for that, they always say yes. And then you average out the total amount that they'd be willing to pay. That's more than they have, okay? And so it's really difficult to get an estimate, but there are ways to do it. You know, there are all kinds of sneaky ways to do it. You can, for instance, find out how housing prices change when there's a risk of new sunny day flooding from sea level rise in coastal properties. And those housing prices reflect what people are actually willing to pay for a house that doesn't flood, or how much less they're willing to pay for when it does. So there are increasingly ways to do this, and it's an active area. But a sense of failed stewardship by an evangelical Christian, that's a tough one. And we're always going to have to deal, in my view, with non-monetized impacts and values that are simply going to be left out of an analysis like this. And if you don't understand that going in and take seriously what comes out, rather than it being just one of many inputs to a decision-making process, you're going to be making a big mistake. All right? So any quantitative analysis like this, I say this is a small subset of the whole problem. And economic analyses are very much in that category. So your valuation scheme obviously requires not just ethical decisions, but also aesthetic decisions. And this is why we have ethics and the humanities in part in this course. Those decisions really are going to matter in valuation, even inside an economic model, and especially outside the economic model. What value should you put on the preservation of the beauty of your favorite natural area, as opposed to the sacred lands of a poor person in Tonga? Now, I put this down not to be cheeky, but just to show you that if you really were going to bring everything that's aesthetic and ethical as a value into an economic analysis, you actually have to know the answer to that question. Okay? You need to know the answer to that question if you're going to be able to do that. And of course, we don't know the answer to that question. It's going to differ from person to person. I don't know how I could begin to figure that out. Right? Almost don't know how. So let's suppose then, engage in the kabuki theater, having decided how to value every environmental investment and every alternative use of the same money in every subsequent year to the decision, and for every person in the world, we then need to translate these measures into utility. How that consumption, all in the same metric of dollars in time t, how that consumption translates into some sense of well-being that we call utility, okay? And where utility is operationally defined. And as Professor Fleurbet said, a utility function that is curvy in this way gives priority to those worst off in consumption. Because it says that utilities increased more by giving an extra dollar of consumption to a poor person than to a rich person. Now, as we're going to see at the end, I want you to flag this in your heads. You're going to see at the end the primary difference between the polar opposites of the economic valuation game, which Professor Fleurbet gave us as Nordhaus versus this guy named Stern, a Yale economist versus a British economist, come up with different carbon prices. That's usually attributed to the pure time discounting that we're going to be talking about. But it turns out their difference is primarily due to a difference about how curvy this function is. And in Nordhaus's case, he assumed it was really curvy, which means, in his analysis, by a back door, that if the rich down the road, everybody's going to be rich down the road because he assumed economic growth. And what that says, if it's really curvy, is the rich won't care about climate damages because they'll be so rich that a small change in consumption, negative change, won't reduce their utility very much. Whereas Stern assumed by having it flatter that that effect wasn't as big. And that's really kind of weird. It's not usually talked about. That the rich aren't going to care about climate change because they're going to be so rich they'll be able to build a house away from the advantages. If I had to guess, I actually have an idea, but I don't know if the idea is correct. My guess would be that the poor care a lot because they can't escape physical harm to themselves, to their families, to their communities from climate changes. And that the rich care a lot because they have comfortable lives and want to preserve the sort of beauty of the planet. They have the luxury to think about that sort of thing. And I think the evidence is pretty strong about that. We're going to talk about environmental Kuznets curve, where as a society becomes richer, typically environmental degradation gets worse and then better. It gets better as people get richer because they actually care more about the environment. So anyway, that's the story. Usually this is talked about as being the curvature, as being something that is leads to less inequality. And I have some just sort of baby animations on this. I have three different utility functions there. A blue one that I call a steely-hearted economist's curve. That is, utility is just directly proportional to consumption. A money can't buy me love one that's curved in the way we talked about last time, and one that's curved in the opposite way, And that's called the elephant in the room. I get happier and happier and happier the richer I get. All right? And the elephant, it refers to the first lecture. Okay, so money can't buy me love. Let's suppose that we're going to divide money between two people while maximizing some of their utilities. And in the first case, I give all the money to one, all the consumption to one, $100, and none to the other. All right, those are the two people there, those two dots. You see that? And that means that the total well-being is this value, 10 utility units, plus 0. So the total well-being is 10. If instead I give half of the money, $50, to each person, then I have two dots right there, and the total well-being is 17. Meaning I get more total well-being because of the curvature from dividing the money equally than I would get from giving it all to one. See that? So that's why, in fact, this curve favors redistribution. Doesn't favor maximizing inequality. It's just that simple. A numerical example shows where that's true, and if you sort of think about it hard, you realize that whenever it's curved in this way, concave down, it will have that property. Meaning it's better to share than to give them all to one if you want to maximize the total well-being of society. So you should strive for equality. If it's on the blue, the original assumption of most steely-hearted economists that happiness equals consumption, then what happens is if you give it all to one, again the total well-being is 10. But if you give half to each one, $50 to each one, the total well-being is still 10. It's 5 plus 5. And so when you have well-being that is utility proportional to consumption, you're blind to these redistributional concerns, all right? As economics was sort of historically. You don't care about equality. And finally, if you were dealing with really greedy people who got happier and happier and happier, the richer they got, and you gave it all to one, the total well-being was 10. And if you gave it to 50-50, the total well-being would be less than 1. And so you would give all of it to the richest person, okay? And that's from a concave up utility function. And nobody really considers these at all right? Nobody really considers these kinds of policies, although one could argue that our tax policy is a little bit like that. Okay, so the choice of the functional form is, as Professor Feuerbach said, the utility of a particular level of consumption, the choice of that functional form is most definitely an ethical decision about redistribution because of those simple little properties we just talked about. Now, this analogy is due to Keon, and I think it works. First thing, I want to now talk about discounting. So if we have some vague idea that there's a relationship between consumption that if you just deal with the easy to monetize parts you can measure, and then you translate that into utility using some ethical assumptions about inequality, and we ignore the parts of the consumption that are difficult to monetize, then that's part of the problem. But there's this second piece that comes into discounted utilitarianism, which is this discounting business. And this comes in economics, I think, partially from interest and economic growth. And certainly the functional forms that are used, I think, come from that entirely. So the idea is, how does interest work? And so most of you know this and have known it forever, but some of you took mathematics, arithmetic, early in your careers in school and have avoided it since then. So I'm going to go through this, all right? So if you have this symbol of dollars, that means like 100 today or some number, how much is it worth in T years if the interest rate is 5%? Well, the answer is in 1 year, you earn 5% interest, which is multiplying the amount of money you put in at 5% interest times 1.05. All right, you add 1 to 5 over 100, you get 1.05. And that's how much it's worth after 1 year. Now, after the second year, you multiplied the amount that you put in originally 2 years ago times 1.05. So it's 5% bigger than it was at the end of that first year. But then you multiply that by another 1.05, meaning you multiply the original amount by 1.05 squared after 2 years. And that's how much money that it's worth. And then after 3 years, you multiply by yet another 1.05, and it's 1.05 to the third. And after 2 years, it's the amount of money you put in times 1.05 to the tenth power. Now, this process, well, let's do the other one first. That's the way that interest works. The time is in an exponent. And inside here is a growth factor, which is 1 plus the percentage interest rate divided by 100. The percentage interest rate is 5. It's 1 plus 5 over 100, which is 1.5. If the interest rate is -2, that's a lousy interest rate. Don't invest in that. It's -2, then it's 1 plus -2 over 100, which is 0.98. And when you power that up to the tenth power, it keeps getting smaller. Just the way when you power up any number less than 1, greater than 0, say a half times a half is a quarter, times a half is an eighth, times a half is a 16th, it gets smaller and smaller and smaller and smaller, and your money decays away. So this is called exponential growth or decay, because the value in your t is proportional to a constant raised to the power t. It's also called geometric growth, but for those of you who are into elementary math, that's because this quantity is equal to e to the log of that times t. All right, but it's the same thing. Geometric and exponential growth are the same thing. Important thing I want you to remember, this thing is growing or decaying exponentially, like many other things. Einstein is alleged to have said that exponential growth is A, the most powerful force in the universe, and B, it's amazing that it isn't illegal. Okay? And it's because exponential growth is what is behind all kinds of explosive properties. It's what makes an A-bomb go off. What makes most chemical explosions go off. Anything like this. And exponential growth, if you invest money wisely, makes you rich. Exponential decay is like radioactive decay. Every year it's smaller by a factor than it was the year before. But the important point is that interest causes your money to grow or decay exponentially with the time in the exponent. That's going to turn out to be significant. Now, the interest rate in this discounted utilitarianism is actually built into the yearly consumption values. Remember, in this business, you have to sum up your discounted future utility. You remember that in all subsequent years. And so to do this sort of analysis, you've got to figure out how much consumption am I going to be able to afford in 2019, in 2020, in 2021, in 2022. And that implies an ability to figure out how your wealth is going to grow. If you're a nation, how the nation's wealth is going to grow. And so it has embedded in it factors like the interest and any other factor that affects exponential growth, which historically is also exponential. When we say that the economic growth rate is 2%, we mean the size of the GDP at the end of the year is going to be 1.02 times the size of the GDP at the beginning of the year. All right? That's what 2% growth means. And economies have historically grown at exponential rates. Now, the exponential rates change, which makes the statement kind of an oxymoron, right? But nonetheless, they are multiplicative processes. And so economists have been, from the beginning, schooled in building exponential growth into sort of everything they do. And in this case, the exponential growth is built in deeply into the construction of the future consumption estimates or function, right? How much consumption are we going to have in some country in 2035? That's an economic model that is run that has exponential growths in it all over the place, okay? Are there any questions about that? Yeah, I think that's, yeah, there's not a lot of information content there. It's just important to understand that exponential growth is embedded all over the place in that product. Now, all factors that cause future changes in consumption should be built into the CT function so that the utility function can accurately represent future utility. We've already talked about that being a problem, but let's just move on. Now, economists also understand that even with those changes in consumption, that people may not care today as much about their future well-being as they care about today's well-being. So there's two uses of today in there, and that's not cumbersome, that's on purpose. What we're going to be talking about is how much do we care today about today's well-being as opposed to tomorrow's well-being. Not tomorrow's well-being tomorrow, I mean how much do I care today about my well-being tomorrow, all right? And versus how much do I care about my well-being today, okay? It's always today that I'm doing the caring. But we're talking about different times in the future that I'm caring about today. And so, because they understand people might not care as much today about their future well-being as they care about today's well-being, they've developed a concept that's like an interest rate. It's called a discount rate. D sub r here, in the notation that Dr. Fourbet was using, except I think he didn't have the r as a subscript, but I did, because they just went to the discount rate. And there's a corresponding discount factor, beta, that he was using, right? And beta is approximately 1 minus dr. So if dr, for instance, is 0.02, like a 2% discount, then beta is 0.98, the number that you would multiply by the money, right? Things like that. Right? So that's the difference between beta and dr. And this isn't exactly correct. This is a good approximation for technical reasons. It's a good approximation for the kinds of discount rates that anybody's really going to ever talk about. So if beta equals 0.95, the discount rate is approximately 0.05, okay? Which is like a 5% discount. It's like geometric decay, 0.95 times 0.95 times 0.95, like 0.95 to the cubic power. That's how you're concerned about the future. It's going to decay away. So here we're going to actually use this in a simple example. I'm going to walk through it. There's a lot of words here, but just focus on them all. I know that almost all of you have this logic in your head and you understand everything, but I want to make sure that everybody really, really gets it because it's really simple. So the discount factor beta is raised to a power t, beta to the t power, just like the interest rate, right, when there's a negative interest rate. And it's the utility value today of 1 unit of utility t years in the future. So in other words, let's suppose beta equals 0.9, meaning this discount rate is 0.1. 1 minus 0.1 is 0.9. It's like a 10% discount rate. If it's 0.9, then 10 units of utility is worth 10 units to you today if you're going to get it now. That is 0.9, the beta, to the 0th power times 10 equals 10, because 0.9 to the 0 is 1. Okay? If you're going to get it in a year, then it's 0.9 to the 1st power times 10, which is 9 units of utility. So if you're going to get the thing in a year, today it's only worth 9 units to you if the beta factor is 0.9. The discount rate is 10%. So the DR is 0.9. All the same thing. If it's going to be worth 8.1 units today if you're going to get it in 2 years, because 8.1 is 0.9 squared, 2 years there, times 10. Right? So it's just like interest. You take the amount that you had last year and you multiply it by the same 0.9. So you have 0.9 to the first times 0.9, which is 0.9 to the second. Just like exponential decay or negative interest. Okay, you see that? It's the same thing as the interest story. And finally, it's worth 7.29 in 3 years. 0.9 to the third times 10. And it's 0.9 to the tth power times 10 in 10 years. So that's how this calculation is working. It's exponentially decaying away your value in the future from the perspective of today. How much do I care today about my value in the future? It says that's exponential decaying away. All right? using that beta factor. So this is exponential. And there's a reason that I think it is exponential. Part of it is the familiarity of exponential growth and decay in economic models. And part of it, as we'll see, is probably just to get a snappy mathematical answer, okay? But what I want to ask you, is this really the way that people value the future? Is this the way you value the future? Do you value it in this way at all? And I have a super simple, kind of a dopey example for you. So I want to ask you how many cookies I'd have to give you a month from now to make you choose that option over one cookie right now, presumingly that you want a cookie, right? You don't have to presume you want a cookie. And the equivalent statement is to say, or what fraction of a cookie would I have to give you today to balance my promise to give you a cookie in 2 days from now? All right? And so what I want you to do is to consider that. Now, I considered actually asking you this question, having people vote and clickers, and there's no time, right? And it doesn't really matter because some of you don't even want a cookie. I tried this out on my wife, and she said, "I don't want a cookie. It's stupid." Okay, all right. So instead, let's just imagine a person for whom the promise of a cookie tomorrow is worth half a cookie today. That's the same thing. Those are equivalent value for that person. So the discount rate per day is a half, right? So the one cookie tomorrow is only worth half a cookie today. And it's because maybe I won't give you the cookie tomorrow. Or you got to find me to get the cookie, or all kinds of reasons why. And maybe you're hungry right now, I don't know. Now for that person, now let's consider with that beta factor of a half, how much you'd have to give them today to balance a cookie you're going to give them in a week. And it would be a half to the 7th power. And that turns out to be 1/128th of a cookie. Now, I'm here to tell you that there is no one who's going to decide that that's equivalent. 128th of a cookie isn't a cookie. It's a crumb of a cookie. You can't even taste the stupid crumb, okay? It's like, good God, no one will do that. You're always going to take it, right? The point is, this doesn't work as we get out into the tail. And it turns out that there is a huge amount of experimental work, mostly with psychologists, that shows that this exponential discounting actually doesn't work as people get far from the event. And instead, their value of the future plateaus. And it's actually caused by a function that is a hyperbolic function. That doesn't matter. But people care more about the distant future today than would be given by an exponential discounting. And that's the take-home point. There's a guy who used to be at the Institute for Advanced Study in the university here in the economics department, named Eric Maskin, who the rat moved to Harvard. But before he did, he won a Nobel Prize in economics. And one of the things he did was he showed why, in fact, probably not just humans, but every non-human animal that's ever been tested discounts hyperbolically. What he showed is that if you don't trust the person, if you're not sure about their rate of return, you should discount in this hyperbolic way. But that's a separate point. The point is, we, as a species, when you measure it, don't discount in this way. But yet, this is what is in the discounted utilitarianism formula. All right? And it gets off, especially further out in time, when the climate damages and the avoided damages from mitigation really start to come in. Now, the point here is going to be the choice of the discount rate is in part of an ethical decision, right? How much value should be placed today on the happiness, not just of yourself in the future, but of other people in the future? And that goes into the calculation. So I have an example here. But this example is busy, but really try to unpack what we're saying here. So consider two different futures. In one, we place a tax on carbon. And this causes future consumption, and they're green because we put a tax on carbon. It's a green future. And this is the consumption on the expected consumption, it's say in the United States or someplace, in 2019, 2020, 2021, and so on. And then we have some utility function. And so this is the utility from 2019, that's the utility from 2020, that's the utility from 2021, and so on. And we're discounting them at rate beta. So today, when we put the tax on carbon, and we actually have to make the decision, we worry about that by a smaller amount for next year's change in utility, right? Because there's a beta to the first power, 2 years from now it's beta to the second. This is discounted utility, right? This is the sum of the discounted utilities that Professor Fourvet was talking about. And we consider an alternative function, which is orange, because we don't put a value on carbon. And so we get different consumption patterns, more climate damages and so on. And we get these utilities. And what we want to do is to compare this green function's total present value of utility, all future utilities with the future being discounted, sum out to infinity, for the green versus the orange futures. And so I've got a stupid little numerical example. And on the arithmetic scale, this is the utility value in year t. The green function goes like this, and the orange function goes like that. But you can't really see it, so I took the logarithm of these numbers. Right? So this is a log scale going from 100,000, that's 1,000, that's 10, that's 0.1, that's 1,000, and so on. This is just the log scale of this. You can see that the utility of the orange one starts out bigger. And it's because people are richer right out of the blocks, okay? Because they aren't spending money on a carbon tax. But after time, the reduced climate damages actually make people richer further out, okay? Richer in a utility sense. And so then the green curve gets above the red curve. Now to turn this into the discounted future utility that is supposed to be used to make the decisions, we have to multiply the value of the green curve times some beta function from a discount rate. And there's the beta function for a 10% discount rate, exponentially decaying away, and there's one for a 5% discount rate, exponentially decaying away less quickly. So we'd have to multiply green for the 5% discount rate times that number, plus green for the next year, times that number, plus green for the 10th year, times the thing for 10 years in, times green for the, plus green for the 20, and so on, right? You'd have to do that multiplication, and do the same thing for red. And if you did, you find out that the present future value of mitigation, if the discount rate is 5%, is 1941 from that formula for the green option, and 459 for the orange, meaning you should put the carbon tax in. You get a higher present value of the utility from that 5% discount rate for the environmental action. But if it's the 10% discount rate, then the future decays away in value more quickly today. And so these early periods where people are richer are more important. And we end up with the net present value being higher for the orange option than for the green option. Yes? What's that? Oh, this is the sum for all future years out to infinity. Okay? And that infinite sum converges only because far out in time has no value because the utility is discounting it away. So this is another weird thing, is that you're actually doing an infinite sum. If you remember infinite sums from some time back in your past. All right. Now it turns out that if you do it over some finite horizon sufficiently long, you get the same answer, right? To a very close approximation. Okay, so the point is that in general, a low discount rate will favor action to mitigate future nexus damages, whereas a high discount rate will tend to put off mitigation in favor of actions that increase utility immediately. So if you have a high discount rate, then being richer sooner matters because you just don't care very much about the future. It's beta that the t gets so small. Okay? And if you've got a low discount rate, you care more about the future. So that tends to be true. And as a result, the choice of the discount rate turns out to be at the heart of ethical and practical debates about the climate mitigation and other, yeah.
What are the factors that cause the discount rate to change over time?
So the discount rate in the classical model doesn't change over time. the discount factor and the discount rate stay the same, but your concern changes because the beta is raised to the Tth power.
But I mean, like the life of the discount rate actually stay the same throughout.
Of course not.
So what factors that cause that to change?
Well, among other things, it's what you have, so what would cause the discount rate to change? Anything that would change what you value, right? So if you changed your religion, you might care more or less about future events than you care today. Right? There are all kinds of things that could cause that. Now, I have a couple of rules about economic models that I want to share with you. Well, first, economists always want a snappy mathematical formula. And this isn't always true, but classical economics, you want a snappy mathematical formula. You want an answer that is nice and snappy and compact. You don't want some big, ugly thing that you can't explain to people. And this 2 is really a corollary that comes from 1. Thus, you want as many things as possible to look like economic growth or compound interest, which are always in the economic model. And that means you're going to explain, and this explains exponential definitions of discounting. So you've got all these exponentials in your model, and it turns out if discounting is exponential 2, all those exponentials together make it possible to derive a snappy mathematical formula. And if you used anything else for discounting, no snappy formula, okay? So I actually think this decision about exponential discounting is the result of mathematical tractability and an ethic that you want a snappy formula. So Ramsey, remember Ramsey here? He went to work on the formula for discounted utility using those 2 rules. All right, and so I'm going to walk you through this, and this is the last hard thing here in the lecture, so I'm going to go through this slow. Ramsey said, suppose that an action causes consumption in year T, C of T, to change by an amount delta T. All right? So Ramsey considered an action and says this is going to change future consumption. Either increase it or decrease it by some amount delta T. It can be positive or negative. So the present utility value of these future changes in consumption are thus equal to this. Let's take a look at it. Change in present utility is the utility of the consumption before the change plus the change in utility. So that's the total now new utility, or new consumption in 2019, and that's its utility. Plus beta to the first power, that's the discount factor, discounting the future value today, what you think about the future. And the consumption in 2020, which is what the consumption would have been before the change plus the change. Plus beta squared times the utility of the consumption in 2021 plus the change, plus ... means forever. Keep doing that, all right? And it turns out that sum will converge, even though there's an infinite number of terms. And it's because this beta is decaying away quickly. And then you want to subtract off what the utility would have been without the change. So the net present value of this decision right now is this sum, according to economics, with the change, and this sum without the change. And you take one minus the other and you say, is it worth it? Did I get bigger or get smaller? Is the difference there negative or positive, right? If it's positive, it means the net present utility is better for the change. It's bigger for the change than it would have been. Now this is gnarly, all right? These consumption values, these deltas themselves come from all kinds of economic modeling. It's complicated, gnarly stuff. But if the consumption growth and discounting are both exponential, and if the initial consumption change, the delta is not too large, then one can derive a snappy formula. And that's what Ramsey did. Which is yet another exponential relationship. And what is that exponential relationship? It's this. Now this is an amazing formula. It says that if all those things are exponential, and if the change is not too big, no matter what else is true, it is also true that the change in the present utility, the infinite sum of those terms, is equal to the delta in every year times some discount factor raised to a power. And this discount factor is not the one we started with. Anyway, it's a different discount factor. And it turns out, this is amazing, because this is utility units, and these are consumption units. And so the translation from consumption, money, to happiness is all built into this factor somehow. Okay? It's all built into this factor. So that was Ramsey's result. He was able to take a problem of social welfare and turn it into a traditional economic problem in which all you care about is money. And all the other stuff is just stuck into one number, that beta dollar sign thing. Okay? So what is the beta dollar sign thing? As before, the beta dollar sign thing is approximately 1 minus a discount rate dollar sign thing. And the discount rate dollar sign thing is Ramsey's formula. That's what Ramsey's formula is. Now, it's actually possible with a moderate amount of mathematics to rederive all of Ramsey's results. I actually did this, okay? And it's not bad if you were like a second-year physics student or something like that, right? If you're second-year engineer, it's fine. If you're not, it's not worth it. But it's not particularly difficult, right? In any case, this is Ramsey's formula. And it says I can stuff all of that inconvenient ethical and other stuff into this number, and that number is just 1 minus that number, and that number is this. And what is this? Well, this is the discount rate from the pure time discounting from before. It's the 1 cookie today versus how much of a cookie tomorrow, right? That's that number. And this is the exponential economic growth rate. And this thing, CIA, is a number that determines the curvature of the social utility function. That's what Ramsey's result is all about. So, how does that work? The CIA is big, as Professor Flerbet said, if the function is curvy like this, and 0 if it's straight. So the discount rate gets big if the CIA is curvy, and not if the CIA is big. So this thing that says my current happiness with the change is going to be worth it, right? Change is going to be worth it depends on how much the future change affects consumption and how that decays away according to this rate. Right? Now, it's interesting that this formula carries embedded within it what I call dueling liberal values. If you care a lot about future generations, a person who really cares about the future environment and climate change, then you want DR to be small. Because remember, if the discount rate is large, your care about the future goes away really fast. That's the pure time discount rate. So you want DR to be small. But if you're a liberal, you're also going to tend to want to reduce income inequality. You're going to want to say that's bad, inequality is bad. A conservative would say, no, you need a certain amount of inequality to maintain economic growth, which lifts all boats. But liberals tend to say, no, we want progressive income taxes and whatnot that reduce income inequality. And to get that, you want CIA to be large, remember? So the curved function promotes higher total utility by sharing the results. That was those red and green and blue curves from before, remember with the dots on them? So liberals should want big CIA and small DR. Big CIA increases this thing. Small DR decreases these little things. These are in tension. The bigger this is, the less you care about the future if you're doing this Ramsey analysis. The bigger this is, the bigger this is, but the bigger this is, so the point is liberals should want this to be small and this to be big, and that sends it in opposite directions. All right? So that's interesting. And when Professor Flerbet talked about these two characters, Nick Stern published an analysis that said, price of carbon, we got to act now. And he made these assumptions. The discount rate, the economic growth rate, and the CIA. Nordhaus, who won the Nobel Prize at Yale, said no, it should be this discount rate, this income inequality rate, and this one. And they came up with two really different numbers. Nordhaus is discounting the future faster than Stern is. But if you ask, why is it different? It's not due really to first order, to the differences between two pure time discount rates. It's due to this big difference between the CIA rates. Most of the difference is actually due to how curvy the formula is, okay? And if you do the calculation, the CO2 price at 70 versus $20, which assumptions leads to 70 and which to 20? Turn on your clickers, hit a number. I just want you to know what you're here. I know what it is. It turns out that Stern came up with $70 for the current value of carbon emissions, and so what part of the tax on it. Nordhaus came up with 20, which is too small to get much action. And the difference, if you sort of look at the discount rate, which is where the action is primarily due to Nordhaus making the more liberal assumption about income. And by having this more liberal assumption, what that did by the back door is say, yeah, we're going to be so rich, we're not going to care about climate change because we're just going to build a different house. Okay, we can easily absorb it. All right, that's my attempt.